So, yeah, I've made you, first of all, I've made you a cute little cheat sheet that you will get when I give you this page on Canvas. But once you go there, you'll be able to be like, click, final review cheat sheet, blah, blah, blah. It'll be in the links. And so I'll give that to you once I release the lecture for the day. And it appears that it does not want to load for me. Let's see if I try it in a new tab. Yeah. I guess everybody's on Canvas right now, probably like the teachers trying to make their tests, the students trying to do all their late work. Canvas hates us all right now. This is, well shoot, I've got it somewhere else if it's really not going to load. It'll be up here eventually though. Here, final cheat sheet.pdf. It's this. You'll get it eventually. Boop. Or maybe it's just Firefox's fault now. Nothing wants to load. Here, open that, please. There you go. So you're going to get this eventually, one way or another. But when Canvas decides to load, you'll get it then. So here's a nice little file with information about pointers, recursion, exceptions, bitwise operations. So I try to make it pretty like the last ones that I made for you. And hopefully you'll find that helpful and useful on the test. So you are welcome. We'll go to that eventually. So I got that. And yeah, before we get to talking about that, let's talk about older stuff that I'm not going to let you forget because you're going to use it forever. So let's go there and let's talk about references first. Okay? So let's talk about references. What are those? A reference is an alias, right? It's another name for an existing variable. It's kind of like a wrapper around pointers. That's what's really going on under the hood. There we go. So yeah, reference is an alias for another variable. And so that means it kind of works like this. You have an existing variable somewhere. You make a normal variable, int x equals 42. And then you come along, and that makes a normal box in memory, right? X holding 42. A reference creates an alias for something that's already there. So like you can say this, int reference y equals x. And so that gives another name to that existing box. You mess with x, you mess with y, it's the same. Okay? So normally you don't make a reference in code like this, just in the body of a function. Normally you use it in a parameter, because that's going to let you pass something in a nice way. So you use reference parameters a lot in functions when you want to touch somebody else's memory. Like you have another function, you want it to mess with this x variable. Or you would like to get the memory savings of not making a copy of something. So references are also good for that. So const references are usually for this second one. And so try to use const references as much as possible. Only take away the const when you really need to mess with the value. Okay? So yeah, let me show you just some examples of that. We'll do a swapping example. I'll show you the way with references that works, right? And the way, call by value way that didn't work. So let's do that. References. I think that's spelled correctly. .cpp. So, yeah, let's make int a equals 42, int b equals 43, and we're going to make a function that's going to swap these guys. So we're going to do the wrong way and then the right way. So we're going to make a swap by value function. That's not going to work. So that's just going to make copies, right? And then we're going to print out a and be so surprised, right, that they're not doing the right thing. Hopefully we're not going to be surprised at all this time. And then I'm going to make the right way with references. Swap by reference. And then I'll have to pass along addresses instead. And then it really will have swapped. Okay, so that's the name of the game. And hopefully it's coming back to us. There's a secret third way, right, is to use pointers. Oh, sorry. No, I was thinking ahead. No, reference doesn't need the address. So the secret third way would look like that using pointers. All right, so let's do swap by value. This way is not going to work. Int x, let's call it x and y. Hopefully remember why it's not going to work. So, so this is going to be a call by value function. It's going to take x and y, it's going to swap them. It's going to be int temp equals x, x equals y, y equals temp. That's your standard swapping code. And this is not going to do anything, right? Because call by value, you're copying stuff. It's like when you call this function, it's setting int x equal to a and int y equal to b, and that's separate places in memory. There's no ampersand, no star, no nothing. These are brand new variables local to the function. So this function is not going to do anything. And so it's not actually going to swap the values. We're going to see no change. But swap by reference, we do it that way, and it will work. So swap by reference, all we got to do to make it work is to put ampersands, int ampersand x, int ampersand y. And now, when I call this function by reference, it's going to set it like this, int ampersand x equals a, and ampersand y equals b, and those are references now. Those are aliases for the existing a and b variables down here. It really will mess with their values, rather than making copies like this one did. Okay? So yeah, there's the code. I don't know, let's do, there's the use of them both. It really will work. So the first way does nothing. There's still 42 and 43. But the second way finally does it. They are 43 and 42 correctly. All right? So call by value just makes copies, doesn't let you touch the original memory, but call by reference allows you to touch that original memory because you're just making a new name for those existing variables. Okay. Any questions about that example? Is it all coming back to us? That's that. Another good example of references is like you're passing a gigantic thing and you don't want to copy it. Maybe you just want to use it. So let's make a giant vector, I don't know, size 1000, holding a bunch of 42s because we love 42. So this will be size 1000, and you do not want to copy this around as you call functions. That wastes a lot of time because C++ has to do a copying, has to run copying code for you, and that's like a giant loop through that giant thing. So the better way is to use const references to get all this memory savings. So let me make a vector down here. Vector of ints, call it v, and it'll be a vector holding 1042s. So that's the secret fill constructor. V is a vector holding 1000 elements, all set to 42. And then I want to do like a sum function. Let's be like cout sum on v, and it just needs to go through v and add up everything. And so let's, in our sum function, I'm going to return an int, right? Not sum. It'll take a vector of ints v, and if I do it like this, it's by value and it's being copied. That's disgusting and a waste of memory. So let's pass it by reference, and I don't want to touch the values, I just want to sum them up, so I'll make it a const reference. So, I don't know, your standard way of going through a vector. Make a res variable, and I'll return that. It'll eventually hold the sum, and then I'll go through every value in v, and be like, I could have sworn I muted that. That's funny. I did say mute, but whatever. Oh, it's the other one. Oh, sorry. Maybe that wasn't even my computer. Sorry. I don't even know. So for int I equals v, plus equals I. Something like that. So I'll sum up everything. Oh, this is a range-based for loop. It's going to go through, you kind of read it as in. So for every int I in v, it's going to go through everything. It's going to give you every int in the vector one at a time. Yeah, that's the alternative is going through every index and doing like v at I. That would take more typing. So I'll do it this way instead. And so it's going through and it's 1042s, and yes, it is correctly 42,000 as the answer. So yeah, it's being passed by constant reference, so we're not allowed to touch it. And so we get a space savings and also a time savings because it takes time to copy it if it's large. C++ is just doing it automatically, but that would have taken a lot of time, and so we're saving time. All right, any other questions about that? That's references. Let's next talk about classes. Object-oriented programming, it's pretty popular. So let's see, what do we got? So yeah, classes are your way to make your own types, right? Make your own types, and you can give it the ability to do stuff. Like you can have it respond to your messages, right? You make objects, as many objects as you want, classes type, and then you can talk to those objects by sending them messages. I think it was there. Now it's all muted, hopefully. Yeah, let's do a couple silly examples. Let's make a stopwatch class using CTime to like output the amount of time that the program has been running since you started your stopwatch. Like it'll have a little start button. And then we can look at the screen of our virtual stopwatch with this get time elapsed method. So that'll work like that. And then I'll show you a really cool character that maybe you didn't read about in your book. Yeah, let's do that. Let's make a stopwatch class. Stopwatch.cpp. And here's what I want to do. I want to make a stopwatch object. And I want to start it. Click the start button on it. It's like we're sending it a message. We're actually clicking a real button. That's what object-oriented programming is all about. And then while true, forever, till the end of time, cout s.getTimeElapsed. I'll do a new line right now, but we'll change that. So okay, stopwatch using CTime. Let's see here. So I want CTime. We're going to use that to keep track of where we are. So let's make our class stopwatch, and it's going to have to like hold on to the start time. Like here's what we want to do to it: public. We have like a void start our stopwatch. Alternatively, you can make the constructor start the stopwatch if you want to make a special constructor. And double get time elapsed because time has decimals, I guess, seconds elapsed. And then private, we want to keep track of how much time has elapsed, and that will depend on which library function we're using. So C library. Oops, where'd that go? C library. CTime. And so, gosh, there's a few ways to do this. We could do clock, which keeps track of how much processor time that the program has been running. It's like in terms of clock ticks. And I think I showed you that once upon a time, maybe. But there's also like a time function that gives you back the current real time. And I honestly don't know if it's going to give you milliseconds or not, which would mess with my... I think that would mess with what I want to do. And then you could use diff time on that. But would that tell me any... Yeah, it's just going to give you whole numbers of seconds, and that's no fun. So what we're going to do is we're going to do clock instead. And this is going to be the amount of time that the program has spent running on the actual processor. And so it's not actually going to be counting real seconds. It's going to be counting how many seconds the program's been actually running. And your computers are running a bunch of programs at once, so it's going to be slower than real 1 second, 2 second, 3 second. Okay, so just prepare for that. We're going to use clock. It's the amount of time the program's been running. That's what we're going to do. So we're going to call this clock function. It gives you back a clock t, and that's like us looking at the clock in the computer. So clock t will be our starting time. I got to save that. All right, so there's that. Get time elapsed should be a const method because it's not going to mess with our starting time, but better start our starting time. All right, start the stopwatch. So let's program that, watch it work, and then I'll show you something cool after that. Stopwatch. Not that this isn't cool. It's just our first example. So to start the stopwatch, just be like set the starting time, remember variable, equal to the result of calling the clock function, which is the CTime library's result of like looking at the current time, how much time the program's been running. And then to get the current time elapsed, how much time it's been that the program's been running on the processor since the starting time, we're just going to look at the clock again. So like look at the time now, clock t current time. And the clock function just gives back a clock t. That's the special type. So look at the time now, and then just like return the difference. Return the difference between the current time and the start time. But that's like an integral type, so you got to do something weird. So what we'd like to do is take this. To get like a double number of seconds, we have to convert clocks to seconds. And there's a clocks per sec constant that we can divide by that will do that conversion for us. divide by clocks per sec, but unfortunately, that is also per sec. That is also an integral type, so it's going to do integer division unless we make one of these sides a double. So we'll static cast this side to a double, and then it's going to do double division, and we'll actually have decimal seconds. So that's the fun thing. So yeah, that's the implementation of our class. There it is. Hopefully that makes enough sense. Those two methods, that private member variable, and then it's going to go off and do its thing, keeping track of the time. So let's see if I can split this usefully, kind of, there. So just going to keep on getting the time elapsed, printing it out. Boop. And so it's printed out, it's very slow, it's not even yet to a second because the program is being swapped in and out. There's a lot of programs running at once on your computer, and so they're not like getting the full time. Like here you see the actual time ticking up in seconds. This is quite slower than that. That's just the amount of time the program is getting on the computer. Boop. And it's pausing a lot because it's printing too. So, yeah. So that's that. It's counting up. That's cool. We made a stopwatch class. It's like pretending to be a real stopwatch. But let's make it a little bit cooler with this \r. Have any of us read about that in our book? It should talk about it, like just briefly. Any of us remember what the \r does? Because we've been using \n a lot. This stands for an old idea. It's called a carriage return. So back in the day, computer terminals, it costs a lot of money to make a screen. And so to interact with a large computer somewhere, your mainframe, you would be sitting at what's called a teletype. And so you'd be sitting at a typewriter, and instead of having a screen in front of you, the output would be on paper. It would be printing the output of the terminal for you on a piece of paper, which is crazy to think about. And so essentially, like modern day terminals are emulating this old concept of a teletype. It's like printing out the screen for you on paper. That's pretty much what's going on. And so these kinds of things, this new line, \n, what that means is like tell the teletype to move the paper down so you can type on a new line. \r stands for carriage return. That is an alternative concept that tells the teletype to go back to the start of the line. So that also exists on typewriters. So here, let me draw a typewriter. I doubt we've ever seen a real typewriter. But here's a typewriter. Hopefully we at least know what they look like. All right, it's a little box with keys, and you press them, and it whacks the page with actual printed text. And so you put your little paper in, and then you start typing. So you type your little keys, and it whacks the paper every time you type a new key. And so you're writing on your line, and eventually it gets to the end of the line. Like every time you press, it moves the paper to the, I guess it's this way, so that it starts typing more to the right. And so the idea is there's a little handle here, and it dings. Have we seen like movies where people are using typewriters? Once you get to the end of the line, the typewriter dings, has a little bell. It's like reminding you to move it back. I guess if it was moving that way, you got to move it. Maybe it's on the other side. I don't know. It's over here. And you got to move it back that way so that you can start typing on the line again, on the new line. And so carriage return means move the carriage of the typewriter back to the start. All right? And every terminal is emulating this old thing called a teletype, and it is pretending to be a typewriter. And so if you send \r to your terminal instead of new line, it's going to do a carriage return. So \r. And so the terminal is going to emulate that and pretend to go and overwrite the existing line. So it's going to send the carriage right back to the start of the line. Virtual idea. And so now it's writing on the same exact line. Isn't that fun? No new lines, just one line. And so, yeah, now you know. Control-C to stop the program. So that's kind of fun to think about. Yeah, so that's a stopwatch example of classes. Any questions about any of that? So I have a much more complicated example now. So this is beautiful. This is a fun example. I think I did a great job coming up with it. So I'm going to make a calculator class. And we are going to model a physical calculator. It's going to be great. All right, so we are going to have the ability to, like, we're going to make a calculator object, and it's got to hold on to some stuff. We'll have to think about that. But we're going to interact with that calculator by pressing buttons. Like, if I want to do 42 plus 55, we're going to make buttons for all that. We're going to make, hey, press the button 4, press the button 2, press the button plus, press the button 5 twice. We're going to simulate a physical calculator. So we're going to have like press plus method, press times method. Won't that be fun? And then to enter numbers, we're going to enter them digits at a time. We're going to have to slowly build up those numbers. And so we're going to have press digit methods. You could have press 1, press 2, but press digit is easier. So think about, before I tell you the secret, think about how you'd build up the number 42. Like when you press the 4, then the 2, how would you start building up the 42? How would you do that? So think about that. We're going to have to worry about that. That's what calculators do. And then like there's an enter button down here to actually do the computation. So press the enter button to actually give back the result. Everything else is void. So that's what we're going to do. We're going to make that. And so, okay, if you think about it long enough, what kind of data does a calculator need to have and hold on to? It's doing operations on 2 numbers, right? So it needs both of those numbers. Those are called operands. It needs operand 1, needs to store that, and it needs operand 2. It's like the 42 and the 55. And it also needs to store what operation it's going to do, right? Operation, somehow. Plus, times, minus, divide. Because you press the plus and then you enter operand 2. It's like you're not ready to do the result yet. You're not ready to calculate the result when you press the plus. You just like got to save it for later for when you press enter. Yeah? So those are the 3 things you need to store if you are a calculator. And that's what like real life calculators need to have memory for. So that's kind of fun to think about. So let's get that started, and then we'll talk about how to make the calculator work. So that's fun for me. Let's see. And then we'll write some tests for it too, because we're cool like that. All right. Calculator.cdp. All right. So what I want to do is I want to do something like this. Calculator C. We've just birthed a brand new calculator. I want to make 42 plus 55 happen. So I'm going to press digit 4, press digit 2. And then like press plus, and then press digit 55. 5, then 5. And then I want to get the answer back. I want to be like C out, C dot, press enter, I guess. That goes and computes the answer, gives it back. That's what I want. So I'm going to need a calculator class for all this. It's got to hold on to your private member variables. We're doing integer stuff, let's pretend. So operand 1 and operand 2 will be integers, and operation. Operand 1, operand 2, and then the operation will store it, let's say, as a character. We can store like the plus character if we're doing the plus operation. We just got to save what we're doing somehow. So our character is nice and small, just 1 byte of information, plus character minus character for if we want to do subtraction, etc. Star and slash. So we'll save the character as the encoding of the operation that we want to do, and then we're going to have our methods. So we're going to need a constructor to like zero everything out, and then we're going to need our press digit method, press digit. And it's really cool if you think about it. Like when you press the digit the first time, it's filling in operand 1. When you press the digit the second time after the operation has been given, now you're filling in operand 2. So we have to somehow in that press digit function, we have to figure out like which one are we doing right now. So think about that. Interesting. Before I show you the secret. And then we want to have buttons for all of our operations. Press plus, minus, times, divide. And then we finally want like press enter, that like goes and does the computation and gives our answer back. So finally something that gives an answer back. Okay, So all those things, those need to be there. And let's make them happen. So let's implement these. So down here we go. Calculator, colon calculator. Just get them all ready. Give them some empty bodies right now. And we'll go from there. These operation ones are going to do something very similar. They're all going to do something very similar to each other. And so there's all the stuff. And let's figure out how to implement it. All right, so here's the secret to make the calculator work, to like build up the digits and then also keep track of like, are we filling in operand 1 right now or operand 2 right now? Here's the secret. Here's what you gotta do. You need a state machine. This is a great example of when you need a state machine to do something. Okay, so first of all, the calculator is, first of all, before we talk about the state machine, let's talk about how to fill in numbers, right? So operand 1, let's say we want to fill it with 123, right? We want to press the 1 button, then the 2 button, then the 3 button. How in the world do we eventually get 123 up in here? Because we're not sure when we stop, right? So what needs to happen is operand 1 needs to start zeroed out, and then once we press the 1, we fill it in with 1. Then once we press the 2, we fill it in with 12. And then once we press the 3, we fill it in with 123. So how do we do that? The secret is math. So you press the 1, you start at 0. You press the 1. What this should do is it should take what was here, shift it over, and then add in the new digit. All right, that's how you build up a number. So take what you were at, change it into a 1, like this, somehow. Change it into go from 1 to 12, then go from 12 to 123. So the secret is the thing that you do every time. It's always like, how do you go from 12 to 123? It's times 10 plus 3. You see the pattern? With the new digit. How do you go from 1 to 12? Times 10 to make it 10 plus the 2, the new digit. And so this is all the same. It's times 10, 0 times 10 is still 0, plus the 1 to bring in the 1. Do you see how that will slowly build up the new number? That's the trick. If you do it 1 digit at a time, you got to do it like that. And so it will start at 0. You press the 1 times 10 plus 1. That's just 1. Press the 2 times 10 is 10 plus 2 is 12. Press the 3, then it's times 10 to make 120, plus the 3, 123. You build up your number. Okay, so that's how you build it. And then you also need a state machine to figure out which number you're trying to build up. So you start in the state where you're trying to build up the first number. Remember this kind of diagram? So you start, your start state for your state machine, for your calculator, is you're trying to build up the first number. And as long as you're typing digits, you're adding to operand 1. All the way to 9. Any of those inputs keep you in that state. You're still building up the first number. What tells you, right, what shifts you over to know when you're ready to fill in the second number is the operation. The second you press the operation, that should inform the calculator that you're ready to type the next digit, the next numbers, or all the digits for the next number. So if you type add, subtract, multiply, divide, then it's time for the second number. We'll be in the second number state. Does that make sense? And so then if you type digits, you should be filling in the second number, operand 2, okay? And then finally, you've built up the first number, you've built up the second number, you've added the operation, you've got all that stored away. When you press enter on the calculator, that's what should happen, right? When you press enter, the calculator should be ready to do a brand new calculation. Get ready to type in the next first number, the next operation, the next second number. Does that make sense? So that's how calculators work. They're just state machines. So let's build this up, and then we'll make some tests to be fun. So, okay, now we know the secret. To encode a state machine, to program a state machine, we have to save what state we're currently in. So like we need to know, are we in the first number or are we in the second number? Because that means we fill in a different operand, right? Operand 1 versus 2. So we need to store our state somehow, and I'll store it as a string. So string state. I'll include the string library for that. And so that's that. And so when the calculator begins its life, we want to build up the operands, right? Starting from nothing. So those need to be zeroed out. The operation can be undefined. It doesn't matter. We're going to fill that in anyway. And then state needs to start out. We need to be ready for the first number. So we need to start the calculator in the first number state. So that's what the constructor does. Set the state to first number. I'll use initializer list. And then operand 1 should be 0, and so should operand 2. Boop. And then you can have an empty body. Cool. So there's your constructor. And then now every time we press a digit, we know which digit we're filling in, which operand we're filling in, 1 versus 2, based on our state, right? Based on our state. If we're in state first number, we're filling in operand 1. If we're in state second number, we're filling in operand 2. Those are the only two states in our calculator. So press digit, you just pressed a brand new digit. Do I add it to 1 or 2? Well, if the state is first number, that means we're adding to the first operand. So add this digit to operand 1 if we're here in this kind of state. So that means we take operand 1, whatever it was, and then we make it times 10 plus the new digit. That's how you build up that new thing one digit at a time, just like you're pressing a real button on a calculator. All right. Otherwise, if we were in the other state, we don't need to check for it, just like pretend that that's the only other option. If we're in this case, if it wasn't first number, it must be second number. So add this digit to operand 2. Take it, multiply it by 10, add in the digit. So that's press digit. That's how we know which one we're adding to, based on our state. And then the operations, once we press the operation, we need to save it away so that we know which one to do later when we calculate. And then we also need a transition from first number to second number. All right. So when we press plus, we need to save our operation. That's a member variable, right? There it is. We'll save it away. Then also our state changes. So when we press the plus operation, we'll save the plus, and then we should also transition to the second number state. So the state should become second number. Also, one thing you could do also is check, make sure, because the only time you can press plus is when you were in the first number state. You should not be able to press plus after you type the second number. Only enter should come after that. So if you wanted to be fancy and ultimately correct and implement this, you would want to put an if statement and make sure you were in the right state when you pressed plus, just like error out if it wasn't in the first number state. But we're just going to be lazy. Assume it's correct. Assume the user's doing the right thing. So minus, save away the minus operation. Now, and advance the state. Same for times and divide. Oops, there. So does that make sense? When you press a operation, that should take you from the first number state to the second number state. So change which state we're in, and then also save which operation we did for later when we go and calculate it, because we're going to need to know that. So there's that. And then finally, when we press enter, that's the bulk of our work, right? Once we press enter, we've built up operand 1 and operand 2. We have those. We have the operation saved as a character. All that's left is to take operand 1, operand 2, and do that operation. Whatever it was. If it was a plus, do addition. So depending on the operation, perform that operation. So I don't know, int result, and I'll eventually return that. So perform the operation when you press enter. So if the operation was the plus, we're saving as characters, right? If it was a plus, then the result is operand 1 plus operand 2, just doing what we encoded. Otherwise, the operation was, if that was minus, then we're going to do result is equal to operand 1 minus operand 2. Yeah? It's not too horrible, right? And then, otherwise, if it was multiplication, we're going to do the result is operand 1 times operand 2. Otherwise, just pretend it's slash. Those are the only options. Then we're going to do division, integer division. Okay? So that's the main bulk of the work that the press enter does, but it also should get us ready for a new computation, because the calculator, you don't just turn it on, use it once, right? So we should go back to the first number state, reset the state of the calculator. We should go back to the first number state, just like our diagram is telling us. So state equals first number. And then, to be ready to build up operand 1 and operand 2 correctly again, we want to zero them out. So make them both 0. And so that's what you want to do in the press enter operation. And so, with all these things built up, you can do a key at a time on our virtual calculator. And it really will do whatever 42 plus 55 is, which is apparently 97. Okay? So I think that's beautiful. That's such a great example of classes. So hopefully you enjoyed that. Are there any questions about that? So constructors, we've got a bunch of methods that model real-life things. That's the whole point of object-oriented programming. You're modeling, pretending that it is a real thing that you can touch. That's easier for us humans to reason about. And so we figured out what kind of information we needed to store to make the calculator work. And then we went off and we implemented all those things. So it's definitely a fun one to study, I would say. So with that, let's turn this into tests, because I want to teach you how to test stuff. Have we talked about anything in our cheat sheet yet? I don't think so. That might be next time. Yeah, so it's there, though. You'll have it after this lecture. But let's make some tests. Let's, instead of like printing out the result, let's like confirm. Let's assert true that the answer is 97. That's what it should have been. So let's steal and assert true from somewhere. I don't know where, so I'm going to search for it. Let's steal it from lecture 15. Lecture 27 TDD example. Cool. So, then that. Oh, come on. There. So give me assert true. There it is. Boop. Steal that. Put it here. So now I got that. And let's turn our main function into a test. So what is 30? This is 31? No, it's not. It's lecture 30. I don't know what I was doing. Let's see. I just didn't. Yeah, I messed up the numbering. Yeah, probably because I originally thought it was wrong. Because of the holiday. So this is secretly lecture 30, isn't it? We would have skipped one. That's funny. Yeah, let's see if I did the same thing for my for my 41 class. No, I did that one right. I just messed up ours. Sorry. Alright, so this is the wrong folder. Let me teach you how to fix all this. So, get out of the folder you wish to rename, and I want to move lecture 31 into lecture 30. Now it's like it never happened. Get back into calculator.cpp, back into lecture 30. Excuse me. So, okay. Now I've got my assert true. Let's turn this guy into a test. So let's make it like, I don't know, void test calculator. Test calculator 1, because we're going to make a couple tests. So let's put all this into the test. And instead of counting, let's assert true. So what do we want to assert? What should be happening when we press enter right now? It should be that when we press enter, the result that we get back should be 42 plus 55, because that's what we're trying to build up, which is 97. And we can like give a name for this test, 42 plus 55 test. And so now we'll call that in our main function. Boop. And hopefully it will pass. Yeah. Yay. So there's that one. Let's make a couple other tests. Let's do test calculator 2, because why not? So let's steal this guy. Should be very similar. Test calculator 2. We'll make a calculator out of thin air. And then let's do, I don't know, 123 times 456. Why not? So there's that. I have no clue what this should be. But the beauty of programming is we don't have to know. It's like, what do we get? It should be whatever 123 times 456 is. There we go. We don't even have to know what the actual answer is. We just got to test that it does the right thing. So it should do that multiplication. So it's some big number. You can check it and hard code it, or you can just ask C++ to do it for you. So that's fun. So that's one test, but also the whole point of pressing enter on our calculator is so we can do more stuff with the same calculator. So let's do more. Let's be like, all right, let's do another calculation. Press digit 7, 8, test all of them. Go to 9. Press minus, 78 minus 90. We'll get all the digits in there. 9, 0. Another thing you could have done in press digit was make sure it was between 0 and 9, but again, we were lazy. And then press enter. Now, 78 minus 90. Again, I don't care what the answer is. Just should be this, whatever that is. And so that's a good combined test, I would say. Do one first calculation, make sure it's doing the right thing, and then make sure the calculator got reset properly so we can do a second one. And again, get the right answer. And what do you know? We're great programmers, and they all pass. So yeah, that's a good example of testing our stuff. Any questions about any of that? Can't forget that. Yeah, if we're happy, let's keep on trucking. So I want to talk about pointers. So now we're ready for the beautiful cheat sheet that I have made for you. So what is a pointer? A pointer is a box. It's its own piece of memory. It just holds the address of some other piece of memory. So like you say int x equals 42, that makes a box of memory, but instead of x, like the computer knows it as an address. That's where it lives, that's its starting address. And so you can make an int pointer, start it out, maybe a special place that has no, never access. So the null pointer is the 0 address. You can start it there if you want. Don't dereference because you get a seg fault. But then you can set p to the address of some existing variable, so it'll set it to that. And then you can go through p, like you got this pointer relationship going on, you can go through it and make it all work. So yeah, remember the symbols, right? Ampersand in a type was reference, has nothing to do with pointers. Star in a type makes a pointer. Ampersand outside a type is a get the address of, so you can like store that address into a pointer. And then star outside of a type was dereference, follow the pointer, and do other things, all right? So that is all that. Remember that ampersand also means bitwise and, so that's kind of disgusting. But now you know. So yeah, pointer is a box in memory that holds the address, potentially, of some other box in memory, at least if you do it right. Okay, so like you got int x equals 42, that's your normal int you know and love. So we got that box, and let's say that lives at address 100 because we love address 100. And then you can come along and be like, all right, int star y, make a pointer to an int, have it hold the address of x, and so that builds another box. The pointer is just a box. Y, it has its own address, like 104 maybe, I don't know. And then it is going to hold the address of x, which is 100 here. So y will hold on to 100, and we draw it like this. X is pointing to y. And then we are good to go. Now we could follow y. We could use y like x by dereferencing. So see out star y, new line, or whatever. That would print, and that looks like an x, sorry. It's supposed to be a star. Star y will print 42 because it will follow the pointer, go to address 100, look at the thing there. Okay, so yeah, let's just have an example of int pointers, int pointer pointers, and go even further than this, of course. I'll deal with that later. So, all right, let's make a new file. We got int x equals 42, int star y equals the, not ampersand, sorry, int star y equals the address of x. So now y points to x, it holds the address, whatever that is. And then we can go even further. Why not do this too, right? Why not make a z variable that holds the address of y, which is 104. And z itself lives somewhere, like lives at address 112, 8 bytes later or whatever. And then that's going to point like that. So what should the type of z be? Well, if y is an int star, and we want to hold the address of an int star, z's type better be int star star. Got to tack on an extra star, just like we did for going from int to the address of a single int. So, all right, int star star z equals the address of y. That works. That's fine. And so now, to get to the 42, there's a million ways to do it, right? You can say x by itself, star y, or star star z. All right, but let's print an address as well. So c out x, c out y itself, that'll print the address of x. And then star y will actually go and follow that address and get to x. And then c out z will print the address of y, because that's what it's holding. Star z will print the address of x, because that's what z is pointing to is holding. And then star star z will go and follow all of that to get to x again. So those are all the potential things that you could want to do with a pointer and print out. Boop. So apparently, we got, of course, 42. The address of x, because that's what y holds, the address of x for this run of the program is apparently this. And then star y, of course, because it's pointing to x, you get your 42. And then z holds the address of y, so apparently this is the address of y. It is right after x in memory, which is fun. And then star that gives us whatever y was holding, which was the address of x. So there it is, printing the address of x again, just like that. And then star star z follows z once to get to y, and then it follows y as well with another star to get to x. And so then we see our 42. Does that make sense? Now that you're not seeing it for the first time, I guess it's not as horrible, I hope. So yeah, the other example that I have is pointers to classes or structs where you have stuff inside. You got to dereference first. Then you can use the dot. So like if you had, you can make a pointer to a vector like this. If you had it like a normal vector, here's your vector v, 1, 2, 3. You can make a pointer to a class, to a vector, some object. Call it VP. But remember that pointers, even if they're to classes, they're just numbers. They're just like, what is the address of this thing in memory, the starting address. So you can't like do a dot on this VP object. What you have to do first is dereference it. Dereferencing VP will get you to V itself, and then you can use the dot. But everybody decided that was too much typing and parenthesization, so they invented the arrow operation, which does the dereference and the dot at the same time. So both of these are equivalent to each other, right? Following a pointer to some object. So let's make a vector, and it'll be like vector int, call it v, equals r1, 2, 3, sure. And then I can totally make a pointer to that vector. What's the type? It's vector int star, right? VP equals the address of v. Looks weird, but you can do it. And then to get like the size of the vector, you can't just say vp.size, because vp is a pointer. It's just a number. You have to get to the vector itself by dereferencing. And because of precedence rules, you have to put parentheses around this dereference, which is kind of disgusting. And so everybody decided that it's easier to make a new operator called the arrow operator that does the exact same thing. So both of those last two lines are equivalent there. And they will both print 3, because that's the size of v itself. Right? So don't forget about that syntax, I guess. You can totally have pointers to objects, just gotta dereference it to get to the object, and that's where you do your dots and method calls. All right. And then just in general, don't you dare forget how memory is arranged, right? The whole point of this, the whole reason that we're talking about pointers is because we want to interact with memory itself. Let's get all this up here, maybe. So all memory is this a giant table. It's a big long table that maps addresses to values. So, like, I don't know, this is what memory looks like. Address, value, it's a table. Every address stores 1 byte. Address 0, you're not allowed to use X. Address 1 onwards, though. 1, you can put a byte there. 2, put a byte there. 3, 4, 5, and put bytes there. Etc., etc. ... You have plenty more addresses after that. And so the idea is, most things take up more than 1 byte. Characters take up a single byte. But like integers, for example, those take up 4 bytes. So how do you store those? How do you think about those? So let's say we have an int called I that holds 42, and let's say that it lives at address 1. It starts at address 1, which means, because it's an int, it takes up 4 consecutive bytes starting at address 1. This is how it's stored. It's taking up addresses 1, 2, 3, and 4 secretly. But we usually think about it as having a starting address. So there's where the 42 is being saved in some binary encoding that's 32 bits long. Okay? So that's what memory looks like. That's where things really live. All right? So we've been drawing diagrams, but it's really just a table that holds addresses to bytes, addresses to bytes. You can go and get a bunch of stuff at a starting address then. So like go and get 4 bytes starting at address 104. Really, it's 8 because it's a 64-bit computer. Go and get 4 bytes starting at address 100 because all ints are 4 bytes long. Pointers, though, are 8 bytes long on modern machines. So yeah, I guess that's pointers in a nutshell. Are we happy with that? Any questions about that? So I want to talk about an application of pointers. So we need to understand those first. So we next have the heap, right? The heap was a great use of pointers. Like you can only talk about things on heap memory using addresses. So you're forced to learn about pointers first. So let's remember that. The heap is a magical place that stores dynamically allocated memory. It's like somewhere in between a local variable and a global variable. It's something you can have live for as long as you need it to. It's memory that you make on the fly. You can have it live as long as you need it to. And you get to say when it gets reclaimed or deleted. But you have to keep remembering the address of it, though. That's the one caveat. So you have to do that. So the heap is this place, and you make stuff on the heap by saying new. New, and then you give the type of thing you would like made for you on the heap. All right? So new int, for example, if you see that somewhere, that will go off onto the heap and like give you a new int, brand new fresh int. Okay? So that's that, and then you have delete as well. And delete bracket if you have an array that you made on the heap that you want to delete. So off we go. So here's how this kind of works. Int star I. So you make something on the heap. You say new, give the type of thing that you'd like, and then you get back a pointer to that thing. So it's an int star that you're getting back. The address of that brand new int that got made for you on the heap. All right. So that line does this. So like here's the stack, and then here's the heap. So the I lives on the stack. Anything with a name lives on the stack. And then it's going to point to something shiny and new. New int made this box right here. You say new int, it makes you a brand new shiny box on the heap. And it gives you back the address of that thing. So maybe this was address 100. And so I would hold 100, and it would know where this thing is through that. Okay? And then you can go and set it. Be like star I, just like any other pointer doing it. Star I equals 42. That stores 42 there. And then you use I for as long as you need. Pass it around between functions. It's like a global variable until you want to delete it. And then once you're done, you say delete I. And so you give the address of the thing on the heap that you want deleted. And that will go here. Reclaim that memory, and now you cannot use I anymore. Dereferencing I becomes undefined behavior, and you may not do anything with that. So you should probably set stuff to null after you delete it. That makes it easier on you. Done. If you were deleting an array of things on the heap that you made for yourself, it's delete bracket bracket though. So let's have maybe an example of that. Oh wait, I'll do that after I talk about memory leaks. So don't forget, like your job, like if you want to have heap memory, you have to remember the address of where that is so that you can delete it later, because it's a memory leak to not delete it. I guess if you want it to last the life of the program, it probably should have been a global variable, but it's okay to not delete it, because once your program ends, all the memory for your program, of course, goes away. But usually you should be a good programmer and delete stuff. Don't lose access to things. If you lose access, that's a leak. So here's a silly example of a leak. So let's say we've got this set up already, and we haven't deleted I yet. So let's say we got this. This is what memory looks like right now. Let's say we got this. We got I pointing to our heap thing that we made 42. Cool. And then let's say we come along and we do this. We make this line. We say I equals new int. Don't know why, but we're going to do that. And so what happens when you say this line, when memory looks like this? Well, new int, okay. That makes a new box in memory on the heap. All right. And then we're changing I. So I is going to hold the address of whatever that is. You see that? So that line just leaked. Assuming we don't have the address of this anywhere else, we just leaked that box of memory, right? Because we lost access to it. We overwrote where I is pointing to. It does not remember where this address is, and you can't really guess it or anything. So it's just stuck. This memory has been leaked. It's going to live for the life of the program, and you can access it. You probably wanted to delete it. Leaked. Okay? So that wastes memory. Eventually, your program will run out of memory if you keep doing stuff like that in a loop. So, yeah. That is the idea. And, like, this is garbage as well when you start out. So that is a memory leak. Hopefully that makes enough sense. We don't want to do that. Okay? So let's just have a silly first example of like taking an int on the heap and storing it. So doing something like this, working with it, and then I'll do a more complicated heap example. Alright, we'll do this. Int star I equals new int. That's exactly what we just did. So I is going to point now. I holds the address of. I points to an int on the heap. And then we're going to say star I equals 42 to set it. And now we can go through it. See out star I, new line. Like use I as much as you need to and then delete it, because you don't need it anymore. So that's the normal way to use the heap. Most likely, you would be passing this around. Oops. That's kind of funny. I don't want that dot there. So most likely you'd be passing this around between functions, because there was no real reason to make this on the heap right now. But this is just a silly example. So there's your 42. And we deleted it. Can't go through I anymore. It's undefined behavior. So that's our first example. Does that make enough sense? Let's do a more complicated one with like making an array of things on the heap. All right, this is a good example of it. A better example of using the heap. So let's say this. Let's have the user input a number that's going to tell us how many ints they want to give us. So we're going to make an array of that exact size dynamically on the fly as the program's running. We don't know up front how many things the user wants to give us, how big of an array the user wants us to make. We'll just make it on the heap once they give us that number, though. So the user's going to give us a number. We're going to make an array that holds that many numbers. And then, just for fun, we're going to calculate the median of that array. Not the average, but the median, which will be fun. So try to think about how you do that as I code up the first bit of it. So, like, you have to ask the user, how big do you want this array? Enter the size of the array. And so we'll get that, which is Cn. And then we want to make an array of that size on the heap. So you say new int. If it's an array of ints, that is, new int, and you give it the size. And so that'll make an array of ints on the heap for you, and it will give you back a pointer to the start of it. And you're going to save that as an int star R. So an array can be, you can store that into a pointer, and you're kind of forced to when you use the heap. New is always giving you back a pointer to the start of this memory that it made for you. And so you can use R like an array. I've shown you that before. That's fine. You got to store it like that. And so then we got to fill in the array. right? So 4 int I equals 0, fill in index 0 all the way to index size minus 1. Enter the next next element. And then like set it. R of I becomes next element. Yeah. So you can use this kind of syntax on a pointer, assuming that really is pointing to an array. It's just contiguous memory. It will do pointer arithmetic like I showed you. It'll make it all work. So after this, we've got the array filled. And now our job is to calculate the median of our numbers. So how in the world, does anybody have any idea about how we calculate the median of some array? Because like here's our array. It's like these are typed, I don't know why I want to do it in green, but I'll do it in green. Say the user type this, 2, 1, 4, 3, 5, a size 5 array. Like how would you go and how would you calculate the median of this array? Do you remember what a median is, first of all? It's like the middle number. And median is not 4, right? Even though that's in the middle of the array. What else is missing? So what is the median of this? 3 now? 2, 1, 4, 3, 5. What would be the median? Middle number. Is there something that we're not doing that would make this so much easier for us, right? The median is 3. Yes, it's you just arrange them. It's 1, 2, 3, 4, 5. The 3 is in the middle. Yeah. So it would be much easier to notice that and to find that if we did it like this, right? If we made it 1, 2, 3, 4, 5, regardless of how the user gave it to us. So do you see how solving for the median screams, you better sort this thing? Yeah? Now we'll make it so much easier because then they're arranged like this, 0, 1, 2, 3, 4. Just like go to this index, index 2, and you'll find the thing. All right? How do you calculate that? Because the size is 5. If you divide by 2, integer division will get 2, 2.5, which becomes 2. So just divide by 2, you've got your middle index. All right? That's how you find the median, usually. What happens if you have 4 things? You have an even number of things. How do you find the median of that? What is the median of 1, 2, 3, 4? Remember? Yeah, it's 2.5. So even if you have an array of ints, the median might be a double. So that's interesting to think about. And then again, you'll sort it, and you'll find the 2 middle indices. These 2 guys, you got to average them. That's how you find the median. So how do you calculate that? So this is size 4 divided by 2 will get you the right middle. Subtract 1 will get you the left middle, and you got to average the 2 values there. So it's always divide by 2. You might have to look a little bit to the left of you if your size is even. Okay, so there's secretly a lot going on when you have to find the median of something. So now we know that. All right. Oops, not that. There. Okay, so double median. Median must be a double, even if it's an array of ints. So first thing we gotta do is sort the array. Get everything in order, because then we have a guarantee about where those median elements are. Algorithm is where sort lives. Boop. And so we'll say sort on R, and the way sort works on arrays, you got to give it the address of the start of the array and the address of 1 past the end of the array, which is R plus size. Just take my word for it. Eventually, I think you can kind of understand it now, but that's what it needs. And then we figure out, like, all right, the median is either the middle index, if there is a middle index, the size is odd, or the middle indices, we need to find both of them and average them together if we have an even-sized array. So, off we go. So if, I always see if it's even or odd. It's like size mod 2 divided by 2 and see if there's anything left over. If there's one thing left over when you divide by 2, that means it must have been odd, right? It does not go evenly into 2, so that must be odd. Odd size, and whenever it's odd, the median index is your size over 2 integer division. So 5 over 2, that is 2.5, so 2. That is the index you want. So middle index is size over 2. And so int mid equals size over 2. And median is therefore array of that mid index. Yeah. Else, if it was even size, oh gosh, even size, you have middle indices now. And all right, so if it's size 4, divide that by 2. That gives you index 2. That's the right middle index. The left middle index is the one to the left of it, one less. So, okay, even size. Middle indices are size over 2, and that's the right middle, and then size over 2 minus 1. All right, so you're like int mid right equals size over 2. I don't need parentheses anymore. Size over 2. And then mid left is either mid right minus 1 or size over 2 minus 1. Parentheses, it's going to do PEMDAS. It's going to do the right precedence order. So you can write it like this as well. And then the median is R of mid left plus R of mid right, all that over 2. And now we got to use parentheses. Boop. And these are ints. Those, gosh, sorry. These are ints. It's going to add them together and make an int. This is an int. We want the 0.5. We need integer division, so 2.0. Or sorry, double division, so 2.0. That'll do it right. And then we want to, now we have the median. See out median. We did it right. So the whole point of doing this on the heap is so that we can delete it once we're done with R. Where are we done with R? Right here. Right before we print the median, we don't ever use R again. So we needed it to calculate the median. We don't need it any longer, any more down these lines. So after we calculate the median, and pretend there was a lot more to do after this, we'd save some memory. We'd have more to use for ourselves later. After we calculate the median, we are done with R, so this is a great place to delete it. So it's not delete by itself, R, it's delete bracket bracket if you make an array, because you got to remind C++ like, oh yeah, even though this is an int star, it's the pointer to the start of a very long thing of ints. It's an array of ints. So delete bracket bracket R, and then you can print your median, and you are good to go. And that is a good example, I would say, of actually using the heap for something non-trivial. So you're getting rid of that memory right when you're done with it, which is perfect. So the size of the array, let's do 5. Let's do our 21435. Boop. And yes, the median of that is 3. And then if I do 1, 2, 3, 4 again, so size 4, 1, 2, 3, 4, it's already sorted. The median is in fact 2.5. Beautiful. So it's another fun program to study, I would say. Any questions about this one? But really, the heap stuff is here. Make the array, use it. Once you're done, immediately get rid of it. Go on with your life. Because if you use the heap down here, it might reuse that space. That's what you want. That'll keep you from running out of memory. So if we're good with that, that is where I want to stop for the day. We will do more stuff, more newer stuff since the second midterm. We'll talk about all that, more newer stuff after or on Wednesday. Okay.